Thanks for having me, guys. When Derek approached me to do this meeting, I was very excited. It's maybe a once in a lifetime opportunity to speak to you guys all the way from Canada, and to Uganda users. So I'm thrilled to be here, and I hope you guys can learn something from my sheet metal design experience. My name is Alex. I'm a certified SolidWorks expert, CSWE. And like I said, I'm located in near Toronto, Canada. So very far away from Uganda, and it's the morning right now, 8 in the morning. So let's look at sheet metal design. I have a shelf that I'm gonna model here in just a minute. But before I do that, I did want to talk about. I wanted to talk a little bit about our company. I think it might be interesting for you guys to see what we do here at Trimec Group, and kind of you know what we sell and how we do our business. I think it might be very interesting for you guys to learn something about that. So, Trimec Group is the overall parent company. I was part of the Javelin company, which was bought out by Trimec, and then there's been other companies that were bought out as well in the last couple of years. We have over 250 engineers. We're located over 50 locations across 6 countries, mainly the US, Canada, the UK, Ireland, and the Nordic countries. So we are involved in many different industries, as you can see here. I've worked with customers that design boats, that design kitchens, that design automotive designs, medical devices, small sensors, whatnot, entire power plants, in the energy sector. So there's a lot of different areas that we're involved in, and we sell a lot of different software to show or to help clients build the products for the market, right? Now, as you'll see in a second here, we don't deal with just SolidWorks, right? So the main idea, the concept behind Trimec as a business is to be involved in all areas of the product development process all the way to production. So that starts from creating an idea and then implementing that product into the market. It involves simulating. So whether it's structural testing or flow, we're doing that in a virtual environment. Whether that's documentation, like creating drawings or assembly instructions or product manuals, we have solutions for that as well. And we have solutions for like production, right? Like we have CAM software, we have ERP, resource management software. So it's not just SolidWorks. Engineering, documentation, and models can be used throughout the business. This is I don't think it's a full list of what software we sell, but it's probably a big portion of it. You see SolidWorks here in the left under the design section. We have CATIA. If you're not familiar, that's more for the aircraft and automotive sector. You have DraftSight, which is a 2D software like AutoCAD, very similar to AutoCAD. We have SolidCAM, which is a CAM software for machining. We have ArtTech and GOM, which are softwares for 3D scanning. So we do also 3D scanning. I'm going to touch on that in a second. We have simulation software, et cetera, et cetera. So like I said, it's not just SolidWorks. There's so much more to our business. We do training courses. So pretty much for all the software that you just saw, we have training courses available, right? Like we have SolidWorks Essentials. That's where designers usually start. It's 4 days, and then all sorts of other different training. So I think it's just interesting for you guys to see. We don't just sell software. We do training. We do services. We sell physical products. So When it comes to physical products, we sell 3D printers. We have the Stratasys line, which is the professional line of 3D printers. They're high performance machines. They can print production ready parts. It's not just small toys that sit on your desk. It's physically capable, strong, functional parts. So depending on your application, there's probably material available. And then we also sell Formlabs, which is more of like a hobby style printer. You can sit on your desktop. There's a wide range of materials, but these are usually smaller machines. They're not as professional. So we do sell 3D printers as well. We 3D print parts for our customers. They come to us and they say, we need this part to be printed. And then we help, we print like 100 or 1,000 parts for them. Arctic 3D scanners, we sell 3D scanners as well. So on one end, we're 3D printing. On one end, we're scanning physical objects in the real world. Why would you want a 3D scan? Well, maybe you want to reverse engineer a part that you don't have a drawing for, right? Or maybe you want to inspect a part. You want to see if it's within the tolerances that the design intent or the design engineer intended. So we have a few different scanners. We have Arctic 3D, which the Arctic 3D Leo is what it's called. It's a lightweight and mobile scanner. You can use it anywhere. It has a hard drive and a battery built in. It stores the scan data inside, and then you can plug it in a computer and retrieve the scan data, work with it to reverse engineer the features, and then get it into SOLIDWORKS, where you can work with that model and change it, modify it, or 3D print it, whatever you want to do from there. Then we have the GOM scanner, which are industrial 3D metrology scanners. So that means they're very precise and they're used for inspection. So 3D scanners and 3D printers and software, we sell a lot of different things, right? And then I don't want to go too much about our business here. I just wanted to give you some information, and then so you guys know what we do. You can get more information on SOLIDWORKS, on 3D printing, on simulation, pretty much anything that we do. We write blogs, daily blogs on our Tech Tips blog. I'm going to copy and paste that link into the chat so you guys can look there. This is free, nothing that you need to buy here. I'll do that at the end of the presentation, actually. But you guys can find articles there on sheet metal. There's hundreds of articles on sheet metal. It's going to help you through common problems or just interesting tips that you might find useful in your day-to-day. Any questions from anybody so far? If you have any questions, feel free to jump in the chat, and then I can get to them, or use your mic. Any questions so far? If not, I'm going to continue. So let's get into sheet metal. But quickly before we start in SOLIDWORKS, let's talk a little bit about sheet metal fabrication and then we'll tie in how SOLIDWORKS sheet metal functionality helps us in the real world, right? So the way I see it, there's 4 different areas or 4 different operations in sheet metal. You have cutting. So you're going to be cutting the flat sheet metal sheets, either using a laser, a plasma, or water jet. There's pros and cons to the different technology. There's pros and cons to the technology that you use. You can also cut material by punching it. So a punching machine, which has different shape punches and dies, will cut out the shape that you want. And there's also forming. So we're creating a shape of the sheet metal. It's no longer going to be flat. We want to form it into a specific design. So we can do that with air bending, folding, rolling. There's other operations as well, but those are the kind of the 3 main ones. And then there's welding, different types of welding. Resistance welding is one that I've dealt with. You can see it in the top right photo here, where we're welding two different pieces together using electric current. And then finally, we're assembling the sheet metal, whether that's with welding or with rivets, PEM nuts, which are kind of like rivets, but then they also have screws, so you can rivet basically a nut into a piece of sheet metal. You can use sheet metal screws. That's the simplest, usually the cheapest option. And then there's tab and slot. So you can fit two sheet metal pieces together with a hole in one and then a tab in the other one, right? So my personal experience, my background was as a product designer or mechanical designer. I worked in the sheet metal industry, and I primarily use two machines. One of them is on the left here, is a laser. It's the Mazak laser from Japan. And then we have the Safan Darley press brake. So this one is for the air bending of sheet metal components. These are the two machines that I mainly designed for and made CNC programs for. So I can speak to the, to the background of these machines and the projects I've worked with and designed for. So traditionally, when you think of sheet metal design, when I joined my previous company, most of our drawings were in 2D CAD, right? There was a 2D CAD file with the formed sheet metal, the flat pattern on the same drawing. And those two were disconnected. They weren't parametric in any way. If I added a hole in the formed part, I would have to add it on each view and then also on the flat pattern. Sorry, Derek, could you see if somebody has their mic on, if you could mute them, maybe? Aside from 2D drawings, right? Maybe we just need a blank size, so we'd shear that and then bend it on the handbrake, all manual, right? Traditionally, also we would have to do calculations on the radius / deduction, because when you're bending a sheet metal part, on that bend, it's actually stretching a little bit. So we have to take the stretch into account, take it away from the flat so that our formed piece is at the correct dimensions, right? Now, the modern approach is in 3D CAD and SOLIDWORKS. We can design sheet metal components in 3D CAD, and we can flatten that part. So the flat and the 3D model are parametrically linked. That means when I add features to my formed sheet metal part, those same features are added in the flat pattern. So it's just a much better way to work, right? You see this assembly on the right. We can design sheet metal in the context of an assembly or in the context of other parts. So we can reference hole sizes to maybe like a diameter of another component, right? So those two are linked. And then we can analyze multiple variations and iterations. So if we want to change designs quickly, we can do that in the 3D CAD environment. It's very easy as opposed to 2D or by hand, right? And then finally, we can virtually test our sheet metal components, whether that is for structural integrity, flow simulation, thermal, whatever it is, we can do that in 3D, right? So SOLIDWORKS and sheet metal design, what are the benefits? Well, SOLIDWORKS has specialized tools for sheet metal design. We're going to see those in just a second. Flanges, bend deductions are done automatically. Flat patterns, we can create those automatically. We can generate DXFs directly from the 3D model, a flat DXF. Those are the most useful for the cutting operation, right? On the right here, you see the top picture. This is a nesting software that came with one of our machines that we use. And so I would export DXFs, and then I would program a bunch of different parts onto one sheet, and then the laser would cut many different parts at the same time, right? So that's nesting. We can also export our models to a CNC bending software. So for the machine that I use, Safan, I would export the 3D model, and then its software would recognize the bends, and then I could create the program for bending. I could design the bending operation. So this bend first, and then this second, and then this third bend. And I could see where the tools on the machine would be. So every time I'm bending each bend, I can see whether or not my part is going to hit the tools or the machine, or if I need to make changes to accommodate the machine that I'm using for, because I want to be designing for the machine that I have and the tools that I have. So it's very easy.
Yes. If you see it.
I'm sorry? Any questions?
Can you sound well? The sun.
The color doesn't matter. The color doesn't. The quality.
Okay. Now, the benefits of sheet metal design in SolidWorks. Why would you want to design in 3D? Again, it's accuracy. We can create accurate parts. We can minimize the prototyping. We know how the part's going to look like before we even design it. We can optimize the material usage, so we can reduce the waste because we're going to be nesting. We're going to be programming a bunch of different parts at the same time. We're going to reduce the material usage. We can simplify the CNC programming. It's very easy. You just drag and drop into your nesting software, and then everything gets programmed pretty much automatically. And because we're doing this, it's much faster to go from the design phase into the production phase, right? Okay, so now that we've covered a little bit about Trimech and manufacturing processes in sheet metal, let's actually jump into SolidWorks and show you how to use the features to design this shelf. So this is a sheet metal shelf with a few different bends. It has holes. It has hemming. And so I'll show you how that's done. This is the general size. This is in inches, guys. So 10 inches, it's going to be about 25 centimeters, right? That's how wide this shelf is. It's going to be 22 gauge aluminum. So very thin. I think that's, oh, I can't do the math right now. It's thin aluminum that we're going to be using. And we're going to be covering a few different sheet metal features that you can see here, right? So the most important, I think, in the end is to get the flat pattern. That's ultimately what that's the goal. So because this part is symmetrical, we're going to design one part, one side of the part, and then we're going to mirror it over and to leverage that symmetry, right? And the process that we're going to use today is called convert to sheet metal. So
I have a question.
Yes, go ahead.
Sorry to disrupt, but I wanted to know, what do you mean by nesting?
Okay, very good question. So you see this picture in the top right?
Yeah.
So this is not SolidWorks. This is a software that comes usually with a CNC laser or a water jet cutting machine. And what it does is it cuts out many different pieces out of a big piece of sheet metal. And so what nesting means is how the software arranges those flat patterns on the sheet metal sheet, right? That's what nesting is. Does that make sense?
Yeah, but okay. Now to my second question: is
Yeah.
the software optimized in a way that it finds the best layout where you have minimal waste, or is it just random? Does it randomly place the designs on the?
Yeah, good question. Typically, I think in the software that I used, which was RAD, it's called RAD Nest, RAD Nest. It had different options. So I actually had a lot of options. But one of them is you can optimize for toolpath, you can optimize for material usage, you can optimize for fastest processing. You can also say in this region of the sheet, I want these parts, like specific parts to be nested, and in this region, I want other parts. So there's control basically on how the nest is created. You can just tell it do it auto, and then it will just nest automatically. Good question.
Oh, okay, thank you.
But this isn't part of SolidWorks, by the way. This is this would be after you export to DXF in another software that comes with your machine.
So you import each individual DXF, or do you?
Yes.
So how do you import the DXF files?
Yeah, typically it would be individually. So you'd export the DXF from SolidWorks, and then in the software you'd import the DXF.
Okay.
Yeah, individually. I think there's some batch processing. I think you could like select a few different DXFs and import them automatically. Yeah, and then you can say if your group of DXFs is a specific product and you have to your order your purchase order is 100, you can put a quantity of 100 and it'll multiply everything by 100.
Okay,
Yeah, it's
thank you.
no worries. Thanks for the question. Good question. So back to the sheet metal design, we're going to use convert to sheet metal today. That's one of the ways you can design sheet metal in SolidWorks. And so it starts off by creating a solid body, right? We're just going to extrude the sketch here, and then we're going to use the convert to sheet metal feature, which allows us to pick faces and edges to define the sheet metal part. And so we're going to end up with the sheet metal body on the right here from an extrude, which is very useful. There's a time and place to use this feature, and today is a good example. So let's jump into SolidWorks. Here is the finished part, right? We can see the sheet metal part here. You can see that SolidWorks has applied the different radii. So we have the radius here, we have a gap, right? This would be very difficult to do without sheet metal features. You would have to surfacing, and it would take a long time, right? So sheet metal features are very beneficial. You also have the hemming, the hem right here. You see that? Actually, let's do. You see the hem. The material is folded in on itself to create a stronger edge. You have double the thickness in this area. So this is a common process as well. Yeah, so sheet metal tab, this is going to be here in SolidWorks. If you don't see it, you can right click here and then find sheet metal. And then you're going to see all of these different sheet metal tools. One of them is the flat pattern. So this is just a different configuration of the part. One of them is the flat pattern, and we can toggle that, right? just with the click of a button, we have this flat sheet metal part. We can then measure the bounding box, right? 5.6, 11, or 17.9, right? So let's close this and let's start designing. So here's my sketch. Here's my sketch, and I'm going to extrude this sketch. And feel free to stop me whenever. I'm just going to do a simple extrude of 5 here. Okay. And we have a solid body, right? Now, convert to sheet metal is the feature we're going to use. You can see the picture here. It's going to create a sheet metal body from a solid body. So let's see how that works. The first thing is a selection of a fixed entity. So it's looking for a face. So we want to say that this face is our fixed face. And then what are the bend edges? So you can do collect all bends. We don't want to do that. We want to have some more control. So we're going to click this guy here and this guy here. Okay. Okay. And we're going to use a gauge table, which is just a table of different thicknesses. So we can pick from different thicknesses. We're using 22 gauge today. So we're going to select 22 gauge. And we can start seeing that things are happening here. The other thing that we want to control is the gap. So this is the default gap for all gaps in our model here. So we're going to do 0.1. This isn't, like an industry standard or anything like that. It's just what I'm doing right now. But you'd have to know what you can do in your manufacturing shop. I've done 0.5 before. I've done 0.1. So it really depends. We're going to do auto relief tear. I'm going to show you what that means in just a second. But for now, let's do that. And we can also change the thickness, reverse. We can go on the outside of the sheet metal face, or we can say that the faces of the body are going to be flush to our sheet metal, right? And then we can also choose the different radius of the sheet metal component. This is dictated by the tools that you're using to bend. So in my previous job, I knew for this thickness of material, I have only, for example, 2 different tools, and I know they can make these 2 radii, because I would bend it, and I would measure it, and I would input that in here. So we're going to just go with 0.3. We're going to click OK. And we've created, our sheet metal body, which we can now flatten. So we can flatten it, but we're not done. So we're gonna continue on here. Okay. So next, we are going to add some material. That's a very common thing. We want to extend something. We want to add material in a certain area. We can definitely do that. And so you can see here, we're going from this to this, right? And then when we add that material, we're going to use something called the sketch bend. We're going to bend the sheet metal about a sketch line, right? So let's do that. Okay, I'm just going to do normal 2. I'm going to sketch, and I'm going to use the S key to pull up my line tool. So we have a closed sketch here, and we just need to define some dimensions. First of all, this line and this line, we need to make them parallel. And then we need to create this dimension. It's going to be 0.75 inches. So around 2 centimeters, for example. And so once that's done, we can click OK. Excuse me. And then base flange or tab. That's the feature we want to use. So if we click base flange or tab, click the sketch. It knows that we're adding to an existing sheet metal body. So it's filling this information for us, like the gauge and thickness. And we're going to merge that result. So once we click OK, we don't see any edges here because it's merged those two bodies. And that feature is now in our tree here, right? We can always go back to it. Just going to turn this off. So our feature is here, right? Now we want to make that bend here. So first we need to activate the sketched bend feature. So sketch bend, and it's asking us to create a sketch or use an existing sketch. So we're going to say this face here, and then we can just stay in this view, select the line, draw the line. Again, we're going to say it's parallel. Make parallel. And again, we're going to do 0.75. We're going to click OK. And now we're right away in the sketch bend feature. And we need to select a fixed face. So which face is not being bent, basically. So this guy here. And then we can see a preview. It's bending the wrong way. But that's fine. We can just click reverse. And we can specify some different options here, like are we bending on the center line of that line, or are we bending material inside or material outside, or do we want that start that bend where the radius starts? But what's the angle? Are we using a default radius, etc., etc.? So there's some options here. Excuse me. So let's confirm that. Well, 90. Any questions so far? Okay. Let me know if I'm going too fast, too slow. This is for you guys. So the next step is to add the flanges on the back here, right? And the interesting part of it is how do we get this? How do we get the two bends to meet at a specific angle, right? So let's see how that's done. And then we're also gonna use break corner. I've used these in my previous job to remove the sharp corners, just because I didn't want people to cut themselves in production, or the customer to cut themselves. So I would round the corner, or I would just chop it off at a 45-degree just like this. And then we're gonna do the hem operation as well. I'll show you how that's done. Okay. Edge flange. I like this being white. You don't need a shadow. Okay. Edge flange. We're going to click an edge, and you can drag this flange, or you can input a specific length here. I believe we're going to input 0.75 again. Oops. 0.75. And but how do we get the second edge? Well, we can just click here again and select the second edge, and SOLIDWORKS is automatically gonna put the cut here. We don't have to do any trimming. It's gonna do that for us, right? We can choose the gap distance. That's the gap distance between these two guys right here. So if I went 0.2, you can see it's much more. 0.1. 0.01 is what I'm going to do. Angle, flange length, it's blind, but you can do up to vertex. So if you are modeling, if you have a vertex that you want to go up to, you can choose that instead of a fixed distance. Excuse me. These options down here are different ways of defining the flange length. Typically, outer virtual sharp is the one to go with, because that's the one that you can measure, like with a tape measure or with a caliper. So this one always made the most sense to me, but I'm sure there's applications for these guys as well. Flange position. So if I go to this view, flange inside means that the flange face is going to finish where this edge is. But if I go bend outside, you see what's happening to the flange? It's coming out from that edge. So depending on your design intent, you want to make sure that you choose the correct flange position. Most of the time I did material inside just because I knew where my flange face would end, right? Any questions on the flange properties? Or does that make sense so far? So let's break the corner. Break corner is a simple feature. You can either do a chamfer or a radius, and all we need is an edge. So we remove that sharp corner. Okay. Hemming. For hem, we need an edge. And so there's different types of hems. Depending on the machine that you have. A lot of these options are machine dependent. But I've used the closed hem, which basically crushes the sheet metal into 2 layers with pretty much no gap in between, right? That's what we want. We're going to do 0.25. Okay, so we're getting there, and we're showing you guys a bunch of different features. The tear, right? So what's happening here, this might look a little bit weird. In the real world, it's not going to look like this, but the material is going to want to tear because of that bending operation. This radius here and this radius here, there's going to be some material that's kind of deforming plastically in that region. You could, if you wanted to get rid of this, you can add, this is not part of the presentation, but you could add a corner relief. So I'm going to show you what that means in just a second. So we're going to get corner relief on a 3 bend corner, and that's this guy here. And we can change the way this looks here, right? So we can add a relief. You can add a relief in this area so that there's no deformation of material in the corner. So typically, this is a good practice unless you want the corner to be closed. I designed sheet metal enclosures where there was airflow going through, and so the corners needed to be tight to reduce the losses of pressure. So, but typically, if it's a structural component like this shelf, maybe you might want to put a relief in there, just like that. Any questions so far? Okay, next we're going to use the hole wizard to define some holes. And then we're going to mirror that body to leverage the symmetry. Okay, hole wizard.
See how much can someone get personally? Then
Sorry, is there a question coming through? Because the audio is choppy. I'm struggling to hear the question. So I've defined 2 points here where I'm going to add the hole using the hole wizard. And so I just input 0.75 divided by 2. We let SOLIDWORKS do the math, and less work for us. So this is just right in the middle of that flange. We're going to add the 2 points. And so now if we go, we have to exit sketch, hole wizard. I don't know if you guys have ever used the hole wizard. If you use it, that's great. If you don't use it, this is basically your machinist's handbook in SOLIDWORKS. So you can define the type of hole. Today we're going to use just a straight basic hole. You could do that with a cut extrude, but there are some benefits to using the hole wizard, like having the access to different standards anti-inch, anti-metric. I'm not sure what you guys use in the Uganda, but you can pick a standard and then you can select what type of hole it is. So in our case, it's a screw clearance hole. And then we can just say 1/4 of an inch is the nominal size. And we can tell it whether that's a close, a normal, or a loose fit. And then it's going to size that hole based on these options. So we're going to say normal. End condition is through all. We can add countersinks near or far, etc. And then SOLIDWORKS picked up that sketch, so the points are already there. Okay. And the cool thing is that you, in the feature tree, you can see 1/4 inch clearance hole. If you just did a cut extrude, it would just say cut extrude 5. You know, that doesn't really give us that much information at a glance when somebody's looking at this. It's much easier to understand what that is. And then when you measure this hole, you're going to see 0.27. So 1/4 is 0.25, but because we said it's a screw clearance hole and it's a normal fit, SOLIDWORKS is adding the 0.02 for the clearance on its own. It's using that from its database, which is why I say it's like a machinist's handbook. So if you're not using that, highly recommend it. Actually, we don't want to go through all. So we want to go back here and say, that's funny. We don't want to do through all. We want to go up to next. Okay. And mirror bodies. We're going to do bodies to mirror this body. We're going to select the mirror face, this face here, right? And there you go. The sheet metal component is done. We can flatten it, right? We can create a drawing of this. So let's create a drawing. Excuse me. Trying to change the scale. Okay, there we go. So there's our drawing. Now, typically what we used to do was on the second sheet, we would go here and we would insert the flat pattern. And there's some bend notes here, like this one's going down, this one's going down 180, that's the hem. So we have some bend notes here, we have bend lines. We could, you know, what we did was we would write a note here, flat pattern. Just like that. And we would also provide overall dimensions. Just for reference. Now, what else can we do here? Well, you know what? I don't like 1/2. be 1/3. And we're gonna move this. What we can also do is if we right click, annotations, cut list properties, we can get these list of properties. There's a lot of information here. Material, if I specified a material, it would be here, the quantity, bounding box, length, and width. So it's telling us how big the flat pattern is. So that's these 2 dimensions. The bounding box, the sheet metal thickness. So that's all in the drawing. The area, and then the blank area. These are really good for estimating the cost. Like our purchasing department would want to know the estimated cost of this part, and knowing how much material goes into it, help them figure that out. There's 9 bends. This was also very important for the cost, because each bend takes up time on the machine. So we would figure out how much time on the machine each part would take, and then from there we know the bending cost, and so on and so forth. 22 gauge. So what we selected from the gauge table is showing up here. And so we have a lot of custom properties that we can get from our sheet metal part, which we would not be able to get if we were just modeling without using sheet metal, right? So there's a lot of different information that you can get from here, and that's just right click, annotations, cut list properties. And that's how you insert this note here. What else did I want to show with drawing? I think that's it, guys. I mean, you know, when we go back to the part and we make any changes to the model, everything gets updated, right? We just extended the length, and we come back here, everything gets extended, and our flat pattern gets extended, our notes update. So you can see the benefit of using sheet metal with SOLIDWORKS as opposed to AutoCAD or whatever else you're using. Sheet metal features are amazing. So that pretty much finishes my presentation here. You know, we've done all these operations. There's a few other sheet metal features that we didn't go over, but these are pretty much the main ones you'll be using. This component can be designed in a different way. You don't have to do the convert to sheet metal. You can model each face. So like I could have started with this face here, and then built out this flange, and then built out this one, and then this one. You could do that if you want as well, but the convert to sheet metal is also a good option. So I thank you guys for coming here, attending Derek's SWUG presentation, and it was a pleasure to teach you guys. I hope you learned something here that you didn't know or see before, and if you did, I'm grateful. I hope to be back doing another presentation maybe one day. So thank you again, and if you have any questions, I'd be happy to answer. I did want to